guys, welcome to Unit 1B Notes F. Today we're going to talk about a neutralization reaction between an acid and a base and how that can be used during titration to determine the concentration of an unknown solution. So the goal of titration is to identify the concentration of a substance, to standardize a solution. In order to do this, you need to be able to compare the volumes of the titrant and the unknown substance. So in IB chemistry and in college in general, it's very common to group experiments by the main kind of data that's collected. And so this main category that titration falls under is known as volumetric analysis. So I definitely want to take a second to emphasize the category we're in right now. Volumetric analysis, obviously an analysis based on volumes. And we do need to know the volumes of both the substance that we're trying to titrate and the titrant itself, the thing that's going to be added in order to go through this neutralization reaction. But you're only going to know the concentration of the titrant, not of the unknown. That's the purpose of the experiment, right? The key behind a titration is a neutralization reaction. So in order to go through neutralization, you would need to have an acid as the titrant if we're trying to identify the concentration of a base or vice versa. Then they'll react, typically forming a water and a salt if you have an arrhenius acid and base. And the assumption is that there is a complete reaction. And so you'll see this question a lot in IB, like just even word problem questions, where we'll ask like what assumptions are made. We're typically assuming there's 100% yield, that there has been a complete neutralization reaction. Of course, there are limitations to consider. This is an experiment, right? So what do we typically need in order to go through our titration calculations, aside from identifying the correct titrant, of course, is to then measure the volumes of the substances being used. But then also a key part here is that we need the chemical equation for the neutralization reaction. So a common mistake with titration questions is to try to use M1V1 equals M2V2. You can't do that because you're not taking into consideration the mole ratio of the acid to base. If they happen to be a 1-to-1 ratio, then you could luck out with M1V1 equals M2V2, but typically you can't do that. We did talk about a shortcut using normality, but the IB questions tend to be broken up into 3 separate sections, making that shortcut more or less obsolete. So let's look at an example question of what a titration calculation is going to look like for IB. It's going to be a word problem, of course, and they're going to give 3 numbers, 2 volumes, and 1 concentration. Volume, volume, concentration. You've got to read carefully to determine which one is the titrant and which one is the thing we're trying to standardize. So the titrant will always be the one where we know the concentration. So that here is the potassium hydroxide. So this is the concentration of the KOH. Whereas the volume given for the hydrochloric acid doesn't come with a concentration, so we know that that's our solution that we're trying to standardize. So let's kind of think about what this would look like in terms of an experiment. We would have our burette going into an Erlenmeyer flask. The thing that we are trying to standardize would go in the Erlenmeyer flask, in this case, our hydrochloric acid. Whereas the titrant, the thing where we know the concentration, is going to go in the burette, the KOH. So one trick I like to use to kind of organize my problem is to write what I know, kind of using this diagram as a guide. What do I know about the KOH? I know that its concentration is 0.500 moles per decimeter cubed. And I know that its volume is this the 25.0 centimeters cubed. And then what's the only thing I know about my hydrochloric acid is that 20.0 centimeters cubed. So now that I've got myself organized, let's think about the neutralization itself. What happens when hydrochloric acid reacts with potassium hydroxide? So this is an arrhenius acid since it has hydrogen, and this is an arrhenius base since it has hydroxide. So the products will always be water and a salt. This is essentially a special type of double replacement reaction. The hydrogen and hydroxide will combine to form the water. And then my other cation and anion will form my salt, in this case, potassium chloride. Now, when you make your new product, you always have to consider the charges, +1, -1, so I don't need any subscript, which in turn means I don't need any coefficients. So here I have my balanced neutralization equation. So I have everything set up, ready to start answering the questions. First question, how many moles of the potassium hydroxide were used in the reaction? So what I have given about potassium hydroxide is the concentration and the volume, but the units are different. And the concentration, I have units of decimeters cubed for volume, and the actual volume was given in centimeters cubed. Remember, centimeters cubed like a milliliter, decimeters cubed like a liter. So I'm going to go ahead and adjust my volume simply by moving the decimal place back 3.0250, so that now I have decimeters cubed. That's going to ensure that when I actually do my calculation for moles, that the units will cancel. So moles essentially is going to come from concentration times volume. If I multiply these two together, my decimeters will cancel out, leaving me with moles. So it's 0.500 moles per decimeter cubed times the 0.025, our volume converted to decimeters cubed, allowing my decimeters cubed to cancel so I can get the moles. So I just need to do 0.5 times 0.025, and I get 0.0125. 3 sig figs, actually. So the thing you got to be careful about is, what was this moles of? Remember, we were coming out of the potassium hydroxide. So I have 0.0125 moles of KOH. This entire thing being the unit. Make sure it's complete. Next question is, okay, how much hydrochloric acid is that? Still in moles, but of the acid instead of the base. So remember, to convert from one substance to another substance, we need a mole ratio. So we are going to start with the given moles, 0.125 moles of KOH, put that over 1, and then whatever's on top goes to the bottom. So we'll have mole of KOH in the bottom of the mole ratio and mole of my acid, HCl, on the top. So those numbers from the mole ratio come from balanced equation. In this case, it was 1:1. So I just also have 0.0125 moles of my HCl. That's the answer to part B. So see how it's very important to include complete units so you know you're answering that specific question. Now we want to know what the concentration of hydrochloric acid is. And although it's not specific, the units IB wants for concentration, unless otherwise specified, which we'll see here in a second, is moles per decimeter cubed. So the given volume here will need to be converted into the IB units to correctly answer part C. So again, just simply moving 3 to the left, the actual volume of the acid is 0.0200 decimeters cubed. So now we're ready to find our concentration with the proper units. So the concentration is moles divided by volume with the right units, right? So on top I've got the 0.0125 moles, and on bottom the 0.0200 decimeters cubed. So I've got my 0.0125 in the calculator. Now I'm going to just divide by 0.02. And I get 0.625 mole dm to the -3 would be the preferred way to show the moles per decimeter cubed as a final answer. So you need your balanced equation. You need to organize your titrant information to start with, and that's going to allow you to solve for the moles of the titrant. Then you need a mole ratio, which is why we needed the balanced equation, to convert from moles of one substance to moles of the other substance, to go from base to acid or acid to base. And then you've got to just watch your volume units before you do your concentration as moles per essentially liter or moles per decimeter cubed. We can get our final answer. But you do need answers for all three along the way. So the normality equation isn't quite as helpful because then you wouldn't be able to answer questions A or B. All right. Let's do one more. And this next one, the mole ratio will not be 1:1. And it's going to ask for some special units in the end. All right. So balanced equation, 0.0125 moles of KOH, 0.0125 moles of HCl, and 0.625 mole per decimeter cubed of HCl for the final concentration. Standardized our solution. All right, on to the next one. This time I've got a volume given of calcium hydroxide, which is my base, and then giving me another volume and a concentration of my acid. So because it gave the concentration of the acid, I know that's what's in the burette, the nitric acid, HNO3. Concentration given for that was 0.0500 mole per decimeter cubed. And then the volume given for that comes back up here, 7.50 centimeter cubed. Then that's going to drop into the Erlenmeyer flask, which would contain the substance of unknown concentration, the calcium hydroxide, CaOH2. Oops. +2 - 1, so I need 2 hydroxides. Watch your parentheses. The only thing I know about the calcium hydroxide is that the volume is 25. No, not 20, 25. There we go. 0.0 centimeters cubed. Okay. So now that I've kind of got things separated, organized, I want to do 2 things before I really get to the math. I want to go ahead and write my balanced equation so I have my mole ratio when I'm ready to use it. And I want to go ahead and convert my units so I don't want to have to worry about that later. It's going to set you up for success. So once you start going, you can just go with the flow. So first, let's do our balanced equation. So we had our calcium hydroxide, CaOH2, remember from the charge, reacting with nitric acid, HNO3, +1 - 1. So we do have a different subscript here, meaning you are going to end up with coefficients on your balanced equation. So we have an arrhenius base because it has OH and an arrhenius acid because it has H. So one of those products is going to be water from the hydrogen and the hydroxide. And then I'm going to take my calcium and my nitrate and combine those together to form my salt. But because calcium's +2, nitrate's -1, I'm going to need 2 nitrates. So then if I look at needing 2 nitrates on the left, that means I need 2 nitric acids. Now 2 hydrogens and 2 hydroxides is going to make 2 waters. So for my balanced equation on this one, I have a 2:1 or 1:2 ratio here of my acid to base or base to acid. So when you convert from part A to part B, now we are going to get a different number. The next thing I want to do is handle my units. And I would go just from centimeters to decimeters on each of these right away, meaning move 3 decimal places back. So 0.00750. Be careful to keep your significant zeros when you do this also. That's going to be decimeters cubed. And we'll convert this one to 0.0250 decimeters cubed. Now we're ready to actually start cranking out the math. So first, starting up top, finding the moles of the nitric acid. I have concentration, I have volume. If I multiply them together, I will get moles. So the concentration is 0.05. Did I copy that right? Yeah. 00 mole per decimeter cubed. And the volume is 0.00750 decimeters cubed. So my decimeter cube cancel, and I'm in moles. So let's put this in the calculator. we've got 0.05 times 0.0075. And I get 3.75 times 10 to the negative fourth moles. Now the calculator does say 0.000375, but IB does have a heavy preference towards scientific notation, so I'm going to go ahead and use that because it's a pretty small number. So that's going to answer my first one. 3.75 times 10 to the fourth. And when I'm writing my final answer, I'm going to specify moles of what? The nitric acid, or HNO3. So I really should have done that here too. Now I want to go from acid to base. So I'm going to need my mole ratio to convert my moles of acid into the moles of base. So starting with the given, 3.75 times 10 to the negative fourth moles of HNO3 over 1. Then I'll put the moles of HNO3 on the bottom, allowing me to convert to moles of the CaOH2 on the top. These numbers in the mole ratio always come from a balanced equation. So you can see it's 2 as the coefficient on the nitric acid. We're going to put 2 on the bottom, that means. So essentially I need to half the moles of the acid. So I'm just going to go ahead and hit divided by 2, and I get 1.8. It actually says 1.875, so I'm going to round that up to 1.88 to stick with the 3 sig figs. And we're still at times 10 to the negative fourth for the moles of the calcium hydroxide. All right, so now let's use this together to find the concentration of my calcium hydroxide. And it does ask for it in very specific units. So I'm going to go ahead and find my moles per decimeter cube and then figure out how to convert it into grams per liter. So first, concentration is moles per volume. And the moles that we just found was the 1.88 times 10 to the negative fourth moles over the volume in decimeters cubed, 0.0250 decimeters cubed. So now I've got my 0.0001,875, like the long version of this that's unrounded in the calculator. It's fine to keep it that way. And then I'm going to go ahead and hit divided by 0.0250. Well, not that you had to type the last 0. And now what the calculator says is 0.0075. But because we want 3 significant figures in scientific notation, I'm going to use 7.50 times 10 to the negative third moles per decimeter cubed of the calcium hydroxide. And on the last question, because it didn't specify units, that would be our final answer. But this time, it actually wants it in grams per liter. So let's look at that conversion. If I start with 7.50 times 10 to the negative third moles over decimeter cubed. What it wants on top instead is grams, but I'm in moles. So mole to gram, we just need our molar mass. So I'm going to go ahead and put moles on the bottom and grams on top. I know 1 mole is equal to the molar mass, and it's actually given in the question here. The relative atomic mass is 74.09, and if it wasn't given, you would just add up the mass of calcium, 2 oxygens, 2 hydrogens, you get your 74.09. And then on bottom, I don't even know if you necessarily need to show this, because a decimeter cubed is the same as a liter. So we could show it just for good measure, 1 decimeter to 1 liter. That way the units technically do cancel, and I have grams on top and liters on the bottom. So now I'm going to take my 0.0075 and multiply it by 74.09 and get my final answer, 5.56 times 10 to the negative third grams per liter. Final answer for part C. So starting off, we had our balanced equation. We organized our nitric acid information and used that to get the moles of nitric acid. use the mole ratio from the balanced equation to convert that into our moles of base. Then with decimeters cubed, we did moles per decimeter. Then we used molar mass to get it into grams per liter for those special units in the end. And we finally standardized our solution and answered all the IB questions along the way. Oops. All right, so we've got our balanced equation. Part A was 3.75 times 10 to the negative fourth moles of nitric acid. Watch your units are complete. Then you got, for the base moles, 1.88 times 10 to the negative fourth moles of calcium hydroxide. Then for our concentration in grams per liter, final answer down here at the bottom, 0.556 grams per liter, or 5.56 times 10 to the negative 2. Should have been to the negative 2 over there, grams per liter on our calcium hydroxide. So I'll take it either way in scientific notation or not. IB does tend to lean more towards scientific notation given the chance most of the time. So anyway, that's it for our calculations on titrations. Our next notes will be on gas laws, notes G. We'll see you there.